Okay, so we were learning optical isomerism until now. So we have some special points here. Suppose you are given a structure like this. Okay, so you could see the structure. Okay, so we know it's a cyclobutane, but here you think like you have a methyl group, and we know there are three, so one should be hydrogen, and in the other one also you have a methyl group like this and hydrogen. Now the question here is whether this given molecule is optically active or not. So it depends upon the orientation of this group. So I can say this can be represented in two ways. Okay, one way is, see here, one molecule I can say, for example, one molecule will have an orientation like this, Me, methyl and hydrogen here. Okay, and the other one will have an orientation like this, Me and hydrogen here. Okay, this is possible. Now let's see another representation. So in another representation, suppose if I am drawing it in this way. Okay, you could see here. So here I have drawn Me with hydrogen, and here I am drawing Me with hydrogen. Now you know that this Me and hydrogen, it's coming out of the plane. Now you tell me which among the following of these two is optically active. Now we can say that here this carbon atom, if you see here, okay, this is one methyl group, one hydrogen, and other is connected to a, what actually? Other is connected to a ring, and this ring has hydrogen and methyl group here. Correct? And if you try to do a symmetry of this ring, you cannot get it because both half are different. And most importantly, there is no plane of symmetry existing within this molecule as such. So I can say that this molecule is optically active. Optically active. Very, very important. But here, if you see this molecule here, I can say this carbon, again, same way I can find it out. I can identify this is a chiral carbon. Even this one, if I am see, one is methyl, one is hydrogen, and other one, if you see, I will draw the plane like this, and I can see this half is dissimilar to this half. So both are chiral, I could understand. But the problem here is what actually this molecule as such has a plane of symmetry. This molecule as such has a plane of symmetry. For example, I can draw that plane of symmetry like this. Like this. So if I divide this into two halves, you can see one half with the Me and hydrogen like this, and other half also has Me and hydrogen like this. So I can say this molecule, even though it has two chiral centers, the molecule is optically inactive. Optically inactive. But in the other case, it is optically active. Why? Because here you could see, if I am trying to divide this into two halves through one plane, you can see in one plane a methyl group is projecting upwards, and in the other plane methyl group is projecting in the downward direction. So both half are not similar. So that's the reason why I say first molecule is optically active and other one is optically inactive. Okay, I hope this point is very much clear for you. Now, we are going to learn the last topic in optical isomerism, that is assigning DL configuration. Okay, here D and L, similar to our RS configuration, there is another way of expressing the configuration at the carbon atom, that is called DL configuration. Don't think here D is dextro and L is levo, not like that. Okay, it has no relation with dextro and levo. Okay, so let us see what is basically deconfiguration. We can say in any configuration, for example, at any chiral carbon, in any configuration at the chiral carbon, okay, the OH or any such group, any functional group is on the right hand side, and hydrogen atom is on the left side. Okay, and also the more oxidized carbon is at the top, okay, and the less oxidized carbon is at the bottom. In that case, we will give a D configuration. And suppose we can say the OH group is on the left side and the hydrogen is on the right side. like the configuration having H and OH at the reverse position in the above case, we will assign that as an L configuration. So very simple, you need to think, first you need to identify the chiral carbon, then you need to see whether any functional group OH similar to that is on the right hand side and hydrogen on the left hand side. Then what you need to check, look at the top and bottom. The more oxidized carbon should be at the top. For example, aldehyde and carboxylic acid, more oxidized is carboxylic acid, so COOH should be at the top and aldehyde should be at the bottom. In that case, we will assign that carbon D configuration. And if the reverse thing happens, that is OH is on the left side and hydrogen on the right side, we will give that as L configuration. So you will understand this more when I take more examples, then it becomes very clear for you. Okay, can we go to examples? Okay, we will take glyceraldehyde as the example and explain. Okay, so it's easy because one time it has in exam they have asked this question, so we cannot ignore this, but this is nowhere mentioned in our NCERT textbook and all, but we need to learn. Okay, so since it is asked one time, for AIMS also this has asked one time, so they can repeat this question, so we will learn this and go. Now I will draw glyceraldehyde, COH, here hydrogen is there, okay, and you have CHO on the top, okay, and CH2OH bottom. Now this is glyceraldehyde, okay. So if you look at this glyceraldehyde, you need to understand that this is a chiral carbon. All four groups are different. Now you need to think whether this is D configuration or L configuration. First thing, we could understand the OH is on the right side, hydrogen is on the left, and comparing aldehyde and alcohol, we know that the oxidized form, which is more oxidized, this one, because this has huge number of hydrogen atom. So surely this is a reduced form. So oxidized form is on the top. Comparing to alcohol, this is aldehyde is more oxidized. Okay, alcohol less oxidized and present at the bottom. So sure, this is what configuration? I can give this as D configuration. Okay, I can say it is D glyceraldehyde. Okay, and if it is, we can assign the priority and find out in what way it is rotating, and we could understand it is, or in experiment we have observed that this is also what actually dextro-rotatory. Then we will also assign plus sign along with that and say this is D plus glyceraldehyde. Okay, don't assume like since it is D I have put plus, not like that. On experiment it is observed that this will rotate the PPL towards the right. Okay, now let's see the other form of glyceraldehyde. You have something like this OH, and you have a carbon here, hydrogen here, okay, and you have aldehyde here, and here you have CH2OH. Now tell me what sort of glyceraldehyde will be that. You could easily understand OH group is on the left hand side, so this will be called L configuration. L configuration. And since OH is on the left, and it is observed that this is levorotatory, so we put minus sign here. Understood? I have taken glyceraldehyde as the example. We can take other examples as well. For example, lactic acid. Wait, I will take lactic acid next. Okay, so if I take lactic acid, the formula is you have COOH on the top and CH3 at the bottom. Okay, and you have H and OH. H and OH. Now again I am seeing the more oxidized group is present at the top and OH group is on the right hand side. Less oxidized is present at the bottom. Since it is on the right hand side, I can give this configuration as D. But it has been observed that this D form of lactic acid is rotating the plane of polarized light in levorotatory fashion. So I can say this is D minus lactic acid. D minus lactic acid. Clear? That's why I told minus or plus depends upon the experimental observation. Okay. Now I can give you next one, L. How the L will looks like? L will have OH on the left and hydrogen on the right, and you have what? COOH on the top and CH3 at the bottom, and I can say this is L plus configuration, L plus lactic acid. See here. Okay, So similarly, we have other thing, serine is there, it's an amino acid, we could see that as well. Okay, so this is lactic acid example. So let me take the third example, serine. Okay, so if I take serine as the example, I can write the formula again. C, hydrogen here, here you have NH2, it's an amino acid, and you have COOH at the top and CH3 at the bottom. This is the configuration. Okay, so if you see here, you could see more oxidized carbon at the top and less oxidized at the bottom, and NH2, the functional group, is on the left side. So I can say this is an L configuration of serine, and this I can say L serine. Okay, so I hope almost this is clear for you. Okay, so next we have a question I have given for you, but this question I want to teach you, like all these what we have seen here is a single carbon system. There can be multi-carbon system, for example in the case of glucose actually. So here the question is, which of the following is the structure of L-glucose? Okay, so here what is the important thing you need to see here is, if there are more number of OH groups on the left side, if there are multi-carbon system like this, you can see here more oxidized carbon at the top and less oxidized carbon at the bottom, and if there are more OH groups on the left hand side, then only that will become L configuration. If there are more OH groups on the right hand side or equal number of OH groups on the left hand and right hand side, then also it is D configuration. Only if there is more number of groups on the left hand side, OH groups on the left hand side, then only this will become L configuration. Now see here, which among the following is L-glucose? Now if I am seeing here, here OH is on the left, here OH is on the right, here OH is on the left, here also OH on the left. So 3 are on the left and 1 is only on the right. So this should be L-glucose. But if you see here, you can see OH group is on the right, here also OH group on the right, here also OH group on the right. So this is a D form. And here also if you see, you can see OH group on the right hand side, OH group on the right hand side, one OH on the left hand side, one OH on the left hand side. If they are equal also, then also it is what configuration? It is D configuration. Please remember this. This is very important for exam. Okay, so I hope this is clear for you, and one more definition we need to look at. That's what we are going to see next. Okay, now we will see the last topic in optical isomerism, or the definition we say epimers. We should understand that what do you mean by the term epimers. Sometimes in options it may appear. Okay, epimers means it's a pair of diastereomers that differ only in the configuration about a single carbon atom. They are said to be epimers. What do you mean by that? For example, if I compare these two, okay, I know in both of them are CHO. Here first carbon OH on right, here first carbon OH on right, and H on the left, here also on the left. Second one I am seeing H on the right, H on the right, and OH on the left, here also OH on the left. Third one I am seeing H on the right, but here OH is on the right. Okay, and fourth one I am checking OH on the right, here also on the right, and H. So that means in between this compound they differ only at one chiral center in the OH position. For example, here they are differing, here they are differing. So such a pair of compounds are called epimers. So we can say these two are epimers. Why we are calling that as epimers? They differ only in the orientation of H and OH only at the one chiral center here. So remaining everywhere the position remains the same. If it is only one place they are differing, such a pair is called epimers. Now let us compare this one and this one. Here OH on the left, okay, but here OH on the right. So here it is differing. Okay, let me take another color for your understanding. So here we can say they are differing. Here also that means they are differing. Okay, but we will compare with the other one. Here OH on the left, here OH on the left, H on the right, H on the right, H on the left, H on the left, OH on the right, OH on the right, H on the left, H on the left, OH on the right, OH on So that means for these two pairs also they differ only at this chiral center with respect to H and OH position. So we can call this as also a pair of epimers. Clear? These two are pair of epimers and these two are also a pair of epimers. Correct? Now if I compare first one and last one, You can see H and OH, but here OH and H, so they are also differing in the first position. And next one OH and H, OH and H, here OH and H, here H and OH. That means more than 2 positions are differing. So first one and last one, they are not epimers. I hope the understanding of epimers is also clear for you. So with this, the complete optical isomerism is completed. Next we will be going to the conformational isomerism. Okay, thank you. So next we are starting with the concept of conformational isomerism. So what is conformational isomerism? I will come to that. So until now we have learned geometrical isomerism, where there is no rotation around carbon-carbon bond is not there. Okay, if this is carbon-carbon bond, there is double bond is present in alkenes and there is no rotation possible. And then we learned optical isomerism, that is totally different, where the compound itself we will keep and PPL, plain polarized light, is passed through that and we will observe its rotation, and based on that rotation we will call that as dextro-rotatory or levo-rotatory, correct? Now next comes the conformational isomerism. Here conformational isomerism means here also the two we can say the conformational isomerism arises due to the rotation of carbon-carbon single bond, because this is applicable mainly in usually in alkanes. Okay, now this, you know, what is this compound? We know actually these two are having the same molecular formula. Okay, but we can say in this compound, this, suppose initially the carbon and its hydrogen atoms are in this plane, correct? Now I can say, like, since single bond is present, axial bond is present, we can rotate this. If it is getting rotated, what will happen? The orientation, this hydrogen, we know that here between two hydrogen atom 120 degree is the angle, so total 360 degree. Now here you can see this is rotated in such a way that now this one will come over here, correct? It has come over here, this one has come over here. So how much it has rotated? So total is 120, so half of that is 60 degree. So I can say that 60 degree you have rotated this compound like this, then it has come like this. Now if you see here, you can rotate it in any angle, 0, 1 degree, 2 degree. So every time its relative position of the hydrogen atom with this one keeps on changing, and we say each of these one as isomers actually. So these type of isomers are called conformational isomers. So we can say the different arrangement of atoms in space that result from the free rotation. Here the different arrangements of atoms are coming due to what? Due to free rotation around CC bond axis, and they are called conformations. Clear? And this angle by which you are rotating, that is called theta, and this is known by the name dihedral angle. Okay, so both will be here dihedral angle. So here in this case this is C2H6, correct? Ethane. So in this case C2H6, the dihedral angle is theta is equal to 60 degree we have rotated, so that we have got this conformation. And we could see here this type of projection, this type of representation is called Sohor's projection. It is called Sohor's projection. And there is another projection that is called Newman's projection, that we will see next actually. Clear? Okay, so I have written a question here. Please go through the question. Which of the following shows conformational isomerism? This is one easiest way. I have given you A, B, C, D and D. And they are asking you which among the following compounds will show conformational isomerism. This is the question. So how to find out that? Let's think logically. In conformational isomerism, what is happening actually? There will be two atoms and there will be a bond in between that, and there will be relative atoms placed here. Okay, and when this bond is rotated, its position of these atoms will change relative to this one. This is basically conformational isomerism, and because of that change in the position of the nearby atoms, we can say different conformers are available. Now let's say with this question, please see it. I can say here option A. You can see, maybe I will take this as one of the atom for rotation. Maybe I can take this hydrogen, this one or this one for other rotation. Suppose it is rotating between this one, then I know that this atom has 3 groups and this has nothing there. So I cannot say relative position of this one with respect to other. So I can say there is no conformers possible for this compound. If you take any atoms, it should be continuous, this and this. you can see, then this will have 3 atoms and this one does not have anything. So that is, I can say this will not show conformation isomerism. Now let's go to this one. Here it is possible, because here if you say take this as one atom, and if I am taking oxygen as another atom, oxygen has 2 lone pair, and if I am going to rotate it, I can say with respect to it has 3 other atoms connected to this one, and this has 2 lone pairs and a hydrogen. So when it rotates with respect to this one, the position of this hydrogen with respect to the lone pair and hydrogen atom keeps on changing. So I can say this has different conformers available. Or the simplest shortcut I can say here is check whether there are 3 continuous bonds are there. Then only conformers exist. For example, in this compound, this is one bond, this is another bond, this is continuous, and this is third bond. So there is a 3 continuous bond is available. Then conformation is possible. Now let's look at water. You can use the same shortcut technique. You can see only continuous 2 bonds are only there. And if I am taking this 2 as the rotation, then this one only have 2 lone pairs and hydrogen. This one does not have anything. If you look at the first option also, you can see 1, 2, only 2 continuous bonds. Here also 1, 2, 1, 2, 1, 2. Anything 2 continuous bonds are only possible. Now let's look at option D. You can see here 1, 2, 3 continuous bonds possible. So I can say this can rotate with respect to oxygen. So this is rotating lone pair, hydrogen, lone pair, hydrogen. Based on its orientation, I can say this can exhibit conformation isomerism. Now let's look at the last one. Here also I can say there are continuous bonds are there 1, 2 and 3. It is possible. So I can say this can rotate between this one and this one. So its position of the hydrogen will change with respect to this one. So this will also show conformation isomerism. So how many compounds will show conformation isomerism? B will show, then D will show, and E will show. So the simplest shortcut is check for 3 continuous sigma bonds. Then if that is present, then it shows conformation isomerism. Clear? Okay, so the next what we are going to learn here is what are the various ways to represent different conformers. There are 2 methods of projections are there. So one is called Sohor's projection. Sohor's projection. And the second method is called Newman's projection. Newman's projection. Okay, so let's see both Sohor's and Newman's projection with the example of ethane. Okay, so let me take, so first we will go with Sohor's projection. Okay, Sohor's projection. So ethane, let us write. What is ethane basically? Ethane we know this is CH3 single bond CH3. Correct? Now if I am drawing the expanded structure, this is H, this is H, this is H, and this is carbon, this is H, this is H, and this is H. Now if you see here 1, 2, 3, 3 continuous bonds are available. So I am sure this will exhibit conformation isomerism. Now next we will see how to draw the Sohor's projection of this one. So Sohor's projection. Okay. So in Sohor's projection, what we do is we will first of all identify which 2 carbon atoms are rotating. So we could understand the bond between this carbon and this carbon is rotating. So we will draw those 2 atoms in an inclined manner. Okay, and we will put an arrow here to indicate this is what is rotating. Now you can draw the remaining atoms that is connected to it. Here it has hydrogen, and here one more hydrogen, here one more hydrogen. And here also you have 3 hydrogen atoms. Draw one hydrogen atom, other hydrogen atom, and other hydrogen atom. Okay. Now this can be rotated so that there can be infinite figures or infinite positions of this one with respect to this one can be obtained. Understood? That is possible. So this is one. This is just I am showing. This is how you represent Sohor's projection. Next we will try to see what is Newman's projection. Okay. So I will take the same example, but let's see that. So next one, it is Newman's projection. Newman's projection. Okay. There is only one. Newman's projection. So in Newman's projection, we use a circle actually. First we draw a circle. First of all, again I am drawing for CH3, ethane. So here what we do is, we draw a circle first, and please understand this circle, you can think like this circle is in three-dimensional view. So this is one carbon and there is another carbon on top of it. So, and these two are like this. But when we see from the front view, we can see only the circle. So that means the two carbon atoms are, first carbon is here, on the back side of this one, other carbon atom is there. So let us assume this is my front carbon. So this has one hydrogen atom, and there is another hydrogen atom, and three hydrogen atoms. Okay. Now we know that there is backside carbon is there, so it has three hydrogen atoms. So let me draw, this can be one figure. So this is one hydrogen atom of backside atom, and you cannot extend this to this one because you cannot see that, that is in the backside. And you have another hydrogen atom like this, and you have another hydrogen atom like this. This is one representation. This can be rotated so that next time you will get hydrogen here, this one will go here, and this one will come here. Like that, infinite positions are possible. Okay, but just to understand, this is called Newman's projection. Clear? So let us see what are the different forms, accepted forms in rotation. I told infinite positions are possible, but mainly two forms are mainly accepted. So this is one form. This is called eclipsed form. This is called eclipsed form. Why? Because here one hydrogen atom is eclipsing the other one. Here also one hydrogen atom is eclipsing the other one. That means one hydrogen atom here, on the back side you have other hydrogen atom. This is also like that. Then next accepted or the named form is this one. Listen here, one hydrogen atom front side one. So this is another hydrogen atom, and this is another hydrogen atom. Now you have rotated this one and you have got this structure. Something like this. Hydrogen atom. This is another one. This is another one. Now if you see here, you could understand here the hydrogen atoms are maximum far away from each other. You could see that. This is the maximum far away structure possible, and this is called staggered form. This is called staggered form. And any structure in between this eclipsed and staggered, for example, now here I can say that this hydrogen atom is lying exactly middle of this one, diametrically opposite to this one. It can be here, it can be here. All those infinite structures in between, they are called skew form or gauche form. Skew form or gauche form. Okay, this is staggered form, this is eclipsed form. And the most stable one here is this staggered, most stable. And the least stable one is eclipsed, least stable. Why? Because here they are very close to each other, just back of this one. So the repulsion, steric repulsion is maximum here. Here they are maximum farther away. They are maximum far away from each other. So here the repulsions are very less. In gauche form, it will be not unstable like this. It will be little more stable than eclipsed, but less stable than staggered. So our order of stability will be, I can say eclipsed, okay, then skew, then comes staggered. Okay. So staggered is more stable than skew, skew is more stable than eclipsed. Okay, so I hope you understood this concept. Next we will try to see what is dihedral angle. I already told when one carbon is rotated with respect to the other one, the angle that is created between the two planes is called dihedral angle. In the case of ethane, to get the staggered from the eclipsed form, what needs to happen? This hydrogen should come here. So we know that this total is 120. So if it needs to come here, means it should move 60 degree. So I can say dihedral angle in the case of ethane is 60 degree. Clear? Next we will try to see the case of butane. Okay? Hi dear students, in my last class we were seeing actually the conformations of ethane. Now let's see, we will draw butane and first see whether conformation is possible. Conformational isomerism is possible for butane. So we know what is the molecular formula of butane. So we know that is CH3, okay, CH2, CH2, CH3. This is the formula. Now if you see here, you can see here continuous sigma bond is there. 1, 2, 3. So it is conformation is possible, that is for sure. Now the next question is between which bonds you want to rotate this. So we can say, let us take symmetrically. So let's say between this carbon and this carbon. So let me say 1, 2, 3, 4. Between second and third carbon, I am going to rotate the molecule. Now how I can represent this? Using any projection we can use. First of all, we see this using Sohoit's projection. So these are the two C bonds. So I will draw that C and I will draw a slanting line and will put the another C. Okay. Now you can see here to this carbon atom what is connected? Two hydrogen atoms are connected. So let me draw that two hydrogen atoms. You can see two hydrogen atoms are connected. And you can see the third one is connected to CH3 molecule. So the third one is a CH3 molecule. Correct? Now let's see to the next carbon atom. Two hydrogen atoms are connected. So let me draw that two hydrogen atoms. Okay, and the third one is a CH3 molecule. So CH3 molecule. So and this is rotating with this carbon. So this type of representation we have learned already. This is called what actually? Sohoit's projection. But the disadvantage of this method is whenever you want to draw different conformers, you need to rotate this and draw different figures. And it is not that easy to understand whether it is staggered, eclipsed. It's not that easy actually. So that's why we always go for Newman's projection. Okay. So let's see in Newman's projection how it looks. Okay. So let me redraw it in a Newman's projection formula. So if you see here, I can say in a Newman's projection, this will be, we know, we will draw a circle. So this represents the carbon, and on back side of this one there is another carbon. So it is like this. So from front view you can see only one hand, but on the back side you have another hand as well. Correct? Now we know to this carbon, I will take this portion as the front side carbon. So to this carbon you have two hydrogen atom. So let me say this is one hydrogen atom and this is another hydrogen atom. And you have the third one connected to a CH3 group. So you have CH3 group. Now this is considering as the backside carbon. To this backside carbon, two hydrogen atoms are there. So let me draw first one, the eclipsed format. So this is hydrogen, okay, and this is another hydrogen. Okay, now if it is like this, surely on the backside of this what will be present? On the backside of this we know CH3 will be present. Now this is called fully eclipsed form. Why it is called fully eclipsed form? Because on the backside of CH3 you have CH3, on the backside of hydrogen you have hydrogen, on the backside of this hydrogen also you have hydrogen. So we call this as fully eclipsed form. Fully eclipsed. And please note here one thing, in a fully eclipsed form the repulsion will be maximum because the groups that are similar are nearby. So there will be huge amount of steric repulsion. So I can say this is the least stable. Okay. Now let's go to the next. We will rotate this maybe. So let's say I am rotating. We know this angle, this bond angle is 120 degree. So let me say I am rotating it through 60 degrees. Okay. So when I rotate through 60 degrees, what will happen? This hydrogen will come here. Correct? This will come here and this will go to this position and this will come to this position. So let's see after 60 degree rotation what is happening. So let me draw it one more time. So you have here hydrogen that is present. Okay. Now here you have. So please understand one is rotating with respect to the other. It is not like both of them are rotating. Okay, so I will fix the front part and we will rotate the back part. So you have CH3 here like this, and the back part it is rotated. So it comes here 60 degree I have rotated. So here hydrogen will come, and when it moves, you automatically this will move. So it will come here. CH3 will come here, and this will also automatically move to this position. So you will have like this. This is what you will get after 60-degree rotation. Now let's see, after 60-degree rotation we can rotate it this further. Actually you can rotate this further. One more time if you are rotating, what will happen? One more time 60-degree if you are rotating, the hydrogen will come here, okay, and you can see this as what you will call this intermediate form. We can say this, some people will say, sir, it is partially staggered. Partially staggered means hydrogen opposite to that CH3 is there. We say fully staggered when this CH3 comes diametrically opposite to this one. The better way is call this as a skew form, intermediate form, skew. Okay, now you need to rotate it one more time 60-degree. Now what will happen if you are rotating it one more time 60-degree? So what will happen? You will get another format. I can say here we will fix this hydrogen and CH3 here. Okay, now when you are rotating 60-degree clockwise again, this will move to here, this will move to here, and this will move to here. So you will get, I can say here hydrogen, okay, and here CH3 will come, and here also hydrogen will come. Here hydrogen will come. Now some students may think like, sir, here one is coming behind the other, right? Yes, but we cannot say it is fully eclipsed. This type of format where hydrogen is behind CH3, it's not CH3 is behind CH3. So this type of eclipse, we call this as partially eclipsed. Partially eclipsed. Okay, this we call it as partially eclipsed. And this will be stable, this will be more stable than fully eclipsed, okay, and then skew. Now we have the last one that we need to draw here is the completely staggered. When we are rotating this one more time 60-degree, this will come to diametrically opposite to CH3. That is called fully staggered. That is the most stable one. So I can rub this, okay, I am rubbing this and drawing that. There is no space actually. So let me say, let me draw the fully staggered. One more time I am rotating 60-degree. So again I am drawing the 60-degree means what you will get, see here. So you can see like this. So you have here hydrogen, okay, here also hydrogen is there, and here CH3 is there. Okay, now rotating 60-degree. So this is rotated 60-degree, so it will come here. So I can say diametrically opposite to this one, you will have CH3. And this will also rotate 60-degree and it will come diametrically opposite to this one. Here hydrogen, and here also you will get hydrogen. So this is called staggered, fully staggered form. And this is the most stable one. This is the most stable because they are diametrically opposite, means they are very far away from each other. So the steric repulsion is very minimum. So what is the conclusion we can draw from these figures? So I can say a simple conclusion, that is here if you see if you are asked to write the stability order, I can say the most stable one is staggered. Okay, after staggered who will come next? After staggered we know skew will come, skew forms. Then who will come? We have partially eclipsed. Okay, then we have something called fully eclipsed. Clear? So this will be the stability order. This will be the stability order. Now please learn something from this. You might have seen, to move from completely eclipsed to staggered form, how much rotation it needs to make, how much angle it needs to make. In fully eclipsed, CH3 will be present here. From there it needs to move around this much. That means it is 180-degree it needs to rotate. So they can ask a question like, from least stable, that is fully eclipsed, to most stable, that is staggered, how much is the dihedral angle, how much you need to rotate? The answer will be 180-degree in the case of butane. But in the case of ethane, we have seen all our hydrogen atoms. So one hydrogen atom moves itself, you will get staggered form. There is no difference between different types of hydrogen atom. So there the angle is just 60-degree in the case of ethane, but in the case of butane it is 180-degree. Clear? that you need to know. And one more point you need to remember, whenever you are rotating this one, the angle between this one, for example, if I am rotating front carbon, the angle between this one is always remaining the same. That is, for example, angle between this is 120 degree. When it is rotating, it is the relative position of this one with the backside carbon atom. That angle, that is called dihedral angle, that is changing. But the angle between this hydrogen atom and CH3 is never changing. It is fixed. That was one time question for NEET. Okay. So I hope you understood this concept. Now let's go to the next one. Okay, so next we are going to see the special case of ethylene glycol. Why ethylene glycol is little bit special? That's what we are going to see. So first of all, we write the formula of ethylene glycol. Ethylene glycol is nothing but CH2OH and CH2OH. We might have seen this. Now we know that there are three continuous bonds, 1, 2, 3. So conformation is possible. So let's say, we will say central. So let's say it is rotating between these two. Okay. Now what are the different ways you can draw the conformational isomerism of this one? So I will give only the Newman's projection. Okay. So let's say this is my carbon atom. Okay. Two hydrogen atoms are connected. So two hydrogen atoms are connected means we can draw like this. This is first hydrogen atom and this is second hydrogen atom. And there is an OH group is connected here. Okay. Now the backside carbon atom, I am taking this one. So there also two hydrogen atoms are connected. So let me say that two hydrogen atoms. Let me first draw the fully eclipsed form. So here hydrogen atom, and here also you have the hydrogen atom, and here you have the OH. So we know this is the fully eclipsed form. So fully eclipsed, correct? Fully eclipsed, and we know this is the what actually least stable. Okay. Here is where not the difference is coming. The difference comes in the next one. Now I am rotating this, for example, by maybe let me say some small angle, maybe say some 10 degrees. So it will come here. I am rotating anti-clockwise. So it will come here, it will come here. So let me draw one intermediate form of this one by rotating it through 10 degrees anti-clockwise. So let me say 10 degree ACK, anti-clockwise ACW. Okay. So how this figure further looks like? It will be like this. You have hydrogen. Okay. And here also you have hydrogen. And here you have OH is present. Correct. Now if you see here, when it is rotated anti-clockwise some 10 degrees, let me say the OH will come here. Okay. And here also it will come, hydrogen will come here. Okay. And here also it will come somewhere here. Correct. Now the most important thing here is, in the case of ethylene glycol, the most stable form is not the staggered. We know how the staggered form, this is a gauche form. I can write this is a gauche or skew form. Gauche or skew. Now let me draw staggered also. How the staggered looks like. So the staggered means you will have hydrogen here. Here also hydrogen. And here you have OH. And in this one you have OH will be just diametrically opposite. Hydrogen will be diametrically opposite. This will also be diametrically. So this is the staggered, completely staggered form. Okay. Staggered form. So I can say here gauche form is being more stable than staggered form. The reason for that is, if you see this one, okay, you have a two OH groups somewhere nearby. So what is going to happen here because of these two OH groups present here? So I can say whenever there is hydrogen, okay, electronegative element and hydrogen, what will happen here? There can be the possibility of hydrogen bonding is possible, right? So I can say here electronegative element, okay, electronegative element, hydrogen, then comes electronegative element. That means this representation, this I am drawing in black line, that is referred to as here the hydrogen bond. Okay, this extra hydrogen bond that is formed in gauche form when they are some 10 degree or 2 degree they are very differing, just they are relative, then it can form this intramolecular hydrogen bond formation. That's the reason why this becomes the most stable. Now, why this is not possible in staggered form? Staggered form, they are very far apart. So, the intramolecular hydrogen bond formation is not possible. So, please listen, whenever you have OH group is connected to two carbon atoms like this, then intramolecular hydrogen bond formation is possible. Suppose if you are removing OH group with the fluorine, then also this is possible. Suppose both groups are COOH. Okay, then also this is possible, because when they are nearby carbon atoms, they can stay like this and form intramolecular hydrogen bond formation. In all those compounds, Gaucher form will be the most stable one. Clear? So I hope this is clear for you. Very, very important. In one of the NEET exam, they have already asked this, but most of the students have marked staggered form as the most stable one. That is not the correct answer in this case. So please remember, whenever adjacent carbon has OH group or COOH group, then they can form intramolecular hydrogen bond formation. Just to check whether electronegative element, hydrogen electronegative element, this formation is there or not in any compound in the nearby rotating carbon atoms, then Gaucher form becomes the most stable. Then some students ask me, sir, why don't fully eclipsed form that? It's not possible, because one is just behind the other one. Here hydrogen bond is there, so it will be laying somewhere distant to this one. So in that case, Gaucher form will give you more easily the hydrogen bonding. That is the reason why Gaucher form forms more easily the intramolecular hydrogen bond formation. That's why this is the most stable in this case. Clear? Okay, next I am going to explain a concept called Bayer's strain theory. Actually, why we need to learn this theory? This is not present in NCERT text, but this is very important. Why, I will tell. So we have understood like the conformation is mainly shown by aliphatic compounds. We have seen ethane, butane, ethylene glycol, all these things, and we understood that one carbon is rotating with respect to the another carbon. So that's why this conformation is happening. Conformational isomerism is occurring. Now we can see, for example, can you think whether for alkenes this conformational isomerism is there? No, because there is double bond is there. So one double bond, you have lobes parallel as well as linear, so it cannot rotate actually. And similarly, cycloalkanes, if you take cycloalkanes with the planar structure, they do not show conformational isomerism. Okay, why cycloalkanes? Because for example, you take here cyclopropane I have shown, and we know that if I want to rotate these two carbon atom, there is another carbon here which is in a ring like structure, so we cannot rotate it. The reason for that is this angle strain. There is a concept called angle strain. So this was discovered by, or this was studied by Bayers actually. So he put forward a strain theory called Bayers strain theory. Based on this theory, they explained that cycloalkanes with the planar structures, they do not show conformational isomerism. And what he told is angle strain can be calculated as, very, very important, angle strain can be calculated as 109 degree, modulus of 109 degree 28 minutes minus the bond angle of the compound divided by the 2. Divided by 2. Now for example, let's calculate the angle strain of cyclopropane. What is happening? 109 degree 28 minutes minus 60 degree by 2. So we can say somewhere around 50 degree divided by 2, that is 25 degree will come as the angle strain for here. Correct? And now let's go to cyclobutane. What you are seeing? Again the angle, bond angle has increased. So 90 minus 110 minus 90, that is 20 degree by 2, 10 angle. 10 degree is the angle strain. Angle strain is decreasing. Now when we go to cyclopentane, you could see 108 degree. So I am substituting 108 degree here. So 1 degree by 2, that is 0.5 degree is the angle strain. It has decreased further. And at the end of the day, if I am going to cyclohexane, I can say the angle strain is almost negligible. Then the question here is, if the angle strain is very less for cyclohexane, whether it could exhibit conformational isomerism. Angle strain is less means one carbon can be rotated with respect to the other. That is the meaning. So the answer is cyclohexane, which is having very less angle strain, can exhibit conformational isomerism. There are special shapes for this cyclohexane. I will discuss that next. But before I coming to that, you should understand why cyclohexane exhibits conformational isomerism. And the other compounds like cyclopropane, cyclobutane or cyclopentane will not exhibit conformational isomerism. Clear? So I can say that here angle strain is maximum in the case of cyclopropane, so the stability is minimum. Whenever angle strain is inversely proportional to stability. If angle strain is maximum, then the stability will be minimum. Coming to here, the angle strain is minimum, then the stability is maximum. Clear? So I hope you got a fair idea regarding what is Bayer's strain theory. Now let's see what are the different conformational isomers and shapes of what we say cyclohexane. Okay. As discussed now, as I told, cyclohexane, the special case of cyclohexane, it can exhibit conformational isomerism. So if you see here, I have written there, cyclohexane is maximum stable. It is based on what theory? Bayer's strain theory. Why? Because it has the minimum angle strain and has non-planar structure is possible. Now if you see the different conformations of cyclohexane, it is not like skew, gauche, not like that. They are special case. That's why the different name of different conformers are chair, boat, half chair and twisted boat. You can see here chair form. So how will you check whether it is cyclohexane? 1, 2, 3, 4, 5, 6 carbons are there and pen. So we can say one valency. So here hydrogen atom will be there, here hydrogen atom will be there. Similarly, every carbon atom has 2 extra hydrogen like this. So this is how the structure looks. Now here also if you see, it has also 6 carbon atoms. 1, 2, 3, 4, 5, 6. This is called boat form of cyclohexane. And next one is called half chair. 1, 2, 3, 4, 5 and 6. Correct? And the last one, that is called twisted boat. Here also you can see 3, 4, 5, 6. This one. And this is not. Okay? This is just moving on top of it. This is underneath. Okay, there is no cross linking, it is moving on top of it and this is going through lower part. So there are 6 carbon atoms like this. So these are the various conformations of cyclohexane. And the relative stability, if you see the stability order is, I can say this is the stability order. Okay, this is the stability order. And who is more stable? Chair form is most stable because here the atoms are very farther away. And twisted boat is the next most stable form, and all these are observed through experiments. Next is the boat form, and last comes the we can say it's not half boat, half chair. It is half chair. Okay, so this is the relative stability. So with this we are winding up the theory discussions of conformational isomerism. So that is completed. Next we will discuss some of the questions. Okay.